In the last video, I showed that we could evaluate real integrals using Cauchy's residue theorem. But those integrals were on bounds negative infinity to infinity, and there are many other real integrals that we can evaluate with Cauchy's residue theorem. This is Complex Analysis by a Physicist, and today I'm going to show you how to evaluate real trig integrals with Cauchy's residue theorem. Okay, so this was what you saw on the title screen, but these are the kinds of integrals that we are going to be able to evaluate with this simple conversion, okay? And when I say trig integrals, I mean integrals that have sines and cosines in them, okay? Or mainly they're functions of sines and cosines. And also these that we're going to be dealing with are on bounds 0 to 2 pi, but in future videos you'll see that that doesn't necessarily matter, but for today's video, we'll just be doing an integral on bound 0 to 2 pi. But we just convert it to a complex integral, and we do that with the following steps here. And so first, we're going to convert our bounds of 0 to 2 pi to a positively oriented circle contour that we're going to call C here in the complex plane, okay? And that's just going to be a unit circle unless we have some sort of radii specified based on looking at our equations. I'll get to that a little bit later. But we'll just convert, like I said, we're just going to convert the bounds to a positively oriented circle contour in the complex plane, and that's just going to be a unit circle, so a circle of radius 1. Then we're going to convert the real variables here into complex, but it's not as simple as last time where we're just changing x to z. This time we're dealing with sines and cosines, so we need to convert those accordingly. We're also dealing with d theta rather than dx, so this is more like a polar integral for the real integral, so we need to also convert that accordingly. And these are the three conversions that we'll use here. So there's cosine. Then there's also another one for sine, which is very similar to cosine. And then also our d theta goes to dz here. Then the last step is that we're just going to evaluate the integral using Cauchy's residue theorem after doing a bunch of simplification and arithmetic. And you'll see once we get into the example. So this is the integral we're going to evaluate today, and we're only going to do one because these can be a little bit tricky and require a little bit more work than previous examples. So just to make sure that this video isn't ridiculously long, I'll do some more examples, at least one more example, in future videos that will be standalone videos. So if you're interested in seeing those, keep up with this playlist. If you're watching this in the Complex Analysis by a Physicist playlist on my channel, it'll just be the next video if it's already up. If you're watching this when this is freshly uploaded, that will come in the next 3 to 5 days. So just pay attention for that. But we're going to evaluate this integral here, and this one only has one sign. So let's start first by converting this integral, okay? And so we're going to convert that, and this is going to become an integral over our closed contour C, which we'll define as mod z equals 1. We could really just easily write this as mod z equals 1, but for simplicity, I'm just going to keep it as C, just for contour. And converting all this over, we're going to get a 1 divided by 2 plus 1 on 2i times z minus z inverse. Really, this is just 1 on z, remember, folks. I'm writing it z inverse just because that's the notation that I think is a little bit easier. And then we're just going to have a dz per iz. Okay. And as you can see right here, how are we going to be able to find any singularities of this thing? You might be asking. Well, we're going to need to do a lot of simplification, and so there's a lot more work, as I said, that goes into this, and a lot more that goes into simplifying these things. to get it into a form where we could actually use residue theorem. So I'm going to try to include a little bit more work with these, because normally I sort of combine a step or two together, and I really want to show you as many steps as possible in doing these, okay? So from here, we just need to simplify. And so let's do that. This is going to simplify down to the integral over mod z equals 1, or just our contour. And this time, we're going to take care of this sort of stuff associated with our dz. So we'll try to get rid of that. And when we do that, we're going to get 1 divided by 2iz plus z per 2 times z minus z inverse, and now just dz. Okay, and now we're going to simplify this further by distributing this z per 2 through. So we're going to get the integral over our contour, and then in our integrand, we're going to get a 2iz, that term remains unchanged, plus z squared per 2 minus 1/2 dz. Okay, and for the next step, what I'm going to be doing is I'm going to be converting these, by sticking a 2 all the way through here, or multiplying a 2 all the way through here, and that's going to continue on the next blackboard. So continuing from before, so from the last one, this is just going to continue. So I'm just going to put some dots here to signify dot, 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 and we'll just do a dot, dot, dot for this. And remember, what I said is I'm multiplying a 2 through here. So we're going to get the integral over our contour of 2 divided by z squared plus 4iz minus 1 dz. And now this is something that we can actually begin to work with, because this is a quadratic in our denominator. We have a z squared, we have a z, and then a z0 term. And you can see that this denominator looks very familiar. This is something that we could actually factor out and begin to try to simplify. Now, I'm not going to show you the steps of factoring, because that's just some complex arithmetic that would be very tedious, and I can almost assure you I would mess up in one way or another. But I will say that when I did this earlier, the reason why I say that is because when I did this earlier on a whiteboard, I messed it up like 2 or 3 times and was like, why am I not getting the roots to work out? But anyways, once I got it to actually go, I did it with the quadratic formula. So I strongly suggest you use quadratic formula for this to get the roots. And you should see that the roots that you should get after quadratic formula is negative 2i plus or minus I times the square root of 3. And let me make that 3 look a little bit nicer, which I just wrote the 3 the same. Okay, that's a little bit better. So negative 2i plus or minus I root 3, okay? And so then actually rewriting this out and fully factoring it, we're going to get the integral over our contour of 2 divided by z plus 2i minus I root 3 times z plus 2i plus I root 3, and then that's just still the dz out there from before. Okay, so we have these 2 roots, and these very clearly give us our singularities here for these z's in these 2 terms, 2 separated terms in the denominator. But this is where this problem really gets tricky, because we need to evaluate whether or not these singularities are within our region of integration. So recall that our contour is just mod z equals 1, or the unit circle in the complex plane. And so we're going to need to test both of these to see if they're in that circle. Okay, and we can do that by taking the modulus squared of these things. But notice that for these roots, they're strictly imaginary. Okay, there's no real term here, so we're really getting a 0 squared plus this term squared, and then because it's the modulus squared, we don't take the square root. So when we do that, let's just let me write this out really quickly. If we take the modulus of negative 2i minus I root 3, modulus squared of this thing, is going to give us mod negative 7 minus 4 root 3, which is clearly going to give us a number that is much greater than 1, which so this is going to fall outside of our region. Even if we take the square root of it, which I guess we did the squared part, but that's probably not the best notation. Anyways, this is not going to fit within our radius of mod z equals 1. Now, for the next one, we're going to have a negative 2i plus I root 3. Modulus squared of that is going to give us a negative 7 plus 4 root 3. And this is a little bit tricky. Plug this into your favorite calculator of choice, and you should see that this is approximately 0.07, which if we take the square root of that, I also forgot the mod bars right there, this is going to give you a negative 0.07 approximately, so the modulus of that, 0.07. So this is, and I messed that up as well. So this is clearly less than 1. And so this singularity is actually the only singularity that we're going to need to find a residue for. The other singularity clearly falls outside of our region, so we don't need to incorporate that when using Cauchy's residue theorem. So now having gone through all of that, now we can actually begin to evaluate this integral with Cauchy's residue theorem. Okay. And now we can use Cauchy's residue theorem, and so this is going to equal 2 pi I times the residue of our function, which I'm just going to call f of z at this point to save a little bit of space, even though I am also writing fairly big, of z equals minus 2i plus I root 3. Okay. Man, my 3s today are just not very legible. Okay, and we can use the limit method of finding this residue. So it's going to be 2 pi I times the limit as z tends to negative 2i plus I root 3 of our function. And remember, we need to keep... didn't even transcribe it right. We need to keep the 2 up top there. I completely forgot about that. Let me make sure. Yeah, I did that. Kept it right on the last blackboard. But anyways, so we're going to get 2 times z plus 2i minus I root 3. Divide that all by z plus 2i minus I root 3 times z plus 2i plus I root 3. These terms right here are going to cancel in the numerator and denominator. And so now we can actually evaluate this limit. So we're going to get a 2 on top, and then on the bottom, we're just going to take this and add it to that. So when we do that, we're going to get a 2 pi I times 2 divided by 2i root 3. After doing some simplification, I'm not going to show that because that's just some complex arithmetic, and my 3s still just are not very legible today. But anyways, you can see that a factor of 2 is going to cancel, and also an I is going to cancel, so we're going to be left with 2 pi per root 3, and I can't even finish it off by writing a legible 3. I was really hoping I could. But this is our solution back to our original integral. Right up here in the corner here. Okay, so that is how you go through and evaluate these real trig integrals with Cauchy's residue theorem. As you can see, there's a lot more work involved, and things get very what's the word? Complicated very quickly. You have a lot of big terms that you're going to need to write out, and it's very easy to get lost in the arithmetic. And so that's why we're really only doing one of these examples in this video. Like I said, I'll do another example in a following video here. But these are also very, very useful. Last time we discussed about physicists and some applied mathematicians using integral tables, and I will say that in this case, with these trig integrals, sometimes the integral table will be a lot faster and more convenient for you. But if you're ever stuck on one of those problems, or if you don't have an integral table at your disposal, or an integral calculator for that matter, you can go ahead and use this method here with Cauchy's residue theorem to find the solution to these kinds of integrals. And we will do another example of this, at least one. So thank you very much for watching. If you have any questions at all, don't hesitate to put them in the comment section down below, and I'll do my best to answer your question, provided I can answer it in the comment section. I have gotten comments before. I will say briefly that really can't be answered in the comment section, and I also, I'm not going to answer questions like, help, I need to evaluate this integral. Like, half the reason why I'm doing these videos is so that you can watch them and learn how to do these on your own and apply them to other situations. But anyways, thank you very much for watching, and I hope to see you again next time. Thanks, guys.